Imagine holding the energy of a star in your hand, not the heat, but the power. What if you had a tiny device that could run your phone, car, and home for a lifetime, no recharging needed? This idea, a personal perpetual power source, is the stuff of science fiction, and our wildest dreams. It's more than convenience. It's about unlocking human potential, solving energy scarcity, and democratizing power for everyone. Science fiction teases us with this vision, a glowing core, more powerful than a power plant, fueling heroes and their worlds. But what if this isn't just fantasy? What if the science behind it is real, happening in the universe right now? The journey from comic book dreams to laboratory reality is one of science's most thrilling stories. Let's explore how imagination and science collide. In Marvel's world, this dream has a name, the Ark Reactor. For Iron Man, it's not just a battery, it's his heart, his survival, and his power. The Arc Reactor is a fictional cold fusion generator, a compact clean energy source that powers everything in the Iron Man's suit. Think about it. Flight, super strength, energy blasts, all fueled by a device smaller than your fist. No battery today could handle even a fraction of that demand. The Arc Reactor's energy output rivals a nuclear power plant, yet it fits in Tony Stark's chest. It's the engine behind every invention in the suit, making the impossible possible. This isn't just about keeping the lights on, it's about enabling a new era of technology. The Arc Reactor is science fiction's answer to the ultimate energy breakthrough. But is there real science behind this fantasy? The Arc Reactor may be fiction, but its inspiration, nuclear fusion, is very real. Fusion is the process that powers the sun, smashing light atoms like hydrogen together to release enormous energy. Unlike nuclear fission, which splits atoms and creates radioactive waste, fusion fuses atoms and produces clean energy. In the sun's core, hydrogen fuses into helium at millions of degrees, releasing the light and heat that sustain life on Earth. Fusion's promise is huge. A tiny amount of fuel can yield massive energy, thanks to Einstein's ERMC2. The fuel, hydrogen, is abundant, and the main byproduct is harmless helium. No greenhouse gases, no long-lived radioactive waste. A bathtub of water could, in theory, power a home for years if we could harness fusion. That's why fusion is called the holy grail of clean energy. But making it work on Earth is a colossal challenge. If fusion is so promising, why aren't we using it yet? Because recreating the sun's conditions on Earth is one of humanity's toughest challenges. We need to heat gas to over 150 million degrees and contain it with powerful magnetic fields. No material can touch it. The leading design is the tokamak, a donut-shaped chamber using magnets to hold superheated plasma. The world's biggest fusion project, ITER, is being built in France, a collaboration of dozens of countries. ITER aims to produce more energy than it consumes, a first for fusion. But these reactors are massive, complex, and nowhere near pocket-sized. We're still learning how to build and control a star on Earth. So, could we ever shrink a fusion reactor to the size of Iron Man's Arc Reactor? Today's reactors are building-sized, not palm-sized, and the engineering hurdles are immense. We'd need breakthroughs in plasma containment, new materials, and perhaps entirely new physics. But history shows technology can shrink. Computers once filled rooms, now they fit in your pocket. Could fusion follow the same path? Maybe, with decades, or centuries, of innovation. The dream of a personal star isn't impossible, just incredibly hard. As long as we imagine it, and physics allows, humanity will keep trying. The quest for unlimited clean energy is too powerful to ignore. Last time we explored the Arc Reactor, the glowing heart of Iron Man's suit, inspired by real nuclear fusion. Fusion is what powers the sun. Tiny atoms like hydrogen fuse under extreme heat and pressure, releasing immense energy. The catch? To make fusion happen on Earth, we need temperatures hotter than the sun's core, over 100 million degrees Celsius. At those temperatures, matter becomes plasma, a superheated gas that no material can contain. So, scientists invented tokamaks, giant donut-shaped reactors that use powerful magnetic fields to hold plasma in place, creating a magnetic bottle. These machines are massive, complex and energy-hungry, like the ITER project in France, which is the size of several football fields. We've made fusion happen for brief moments, but sustaining it and getting more energy out than we put in remains a colossal engineering challenge. The goal is ignition, a self-sustaining reaction that produces continuous energy. Today's reactors are our first steps, teaching us how to build a star on Earth. But to reach something like an Arc Reactor, we need a revolution in design and thinking. The challenge isn't just scientific, it's about making fusion practical, compact, and affordable. We know fusion works, now we need to shrink the star in a bottle. The quest for a true Arc Reactor is just beginning. What if we could achieve fusion without extreme heat? That's the dream of cold fusion. In 1989, two chemists claimed they'd done it at room temperature, sparking global excitement. But their results couldn't be reliably reproduced, and cold fusion faded into obscurity. Still, a few researchers persisted, rebranding the idea as low-energy nuclear reactions, or LENR. The hope, certain metals, like palladium, might create tiny pockets of pressure that allow atoms to fuse without massive heat. If proven, cold fusion would mean media group, miniature clean energy reactor concept, hands-holding glowing model of atomic nucleus, clean, futuristic city powered by sustainable energy, inches stock, distribute equally, small, safe, limitless energy, no emissions, no radioactive waste. It remains unproven, but the pursuit continues, driven by the question, what if there's a shortcut to fusion? The dream of cold fusion is a reminder that breakthroughs can come from unexpected places. For now, the world's focus is on making hot fusion practical. While cold fusion remains elusive, a new wave of private companies is reimagining fusion energy. Startups like Helion Energy and Commonwealth Fusion Systems are racing to build smaller, cheaper, and faster reactors. Helion's approach: smash plasma rings together at 1,000,000 miles per hour, aiming to capture electricity directly from the fusion reaction. Commonwealth Fusion is betting on powerful new superconducting magnets, making reactors far more compact than traditional tokamaks. These innovations could shrink fusion plants from stadium-sized giants to something that fits in a building. Unlike government megaprojects, these companies move fast, blending scientific rigor with startup ambition. They're not just building experiments, they're building prototypes for real-world power plants. The competition is fierce, and the stakes are high, clean, limitless energy for the planet. These are the new star builders, and they might just succeed where others have stalled. The fusion race is on. The ultimate goal is to shrink fusion technology from massive reactors to something practical and widespread. Commonwealth's new magnets could make reactors 40 times smaller than ITER, yet just as powerful, a revolutionary leap. Helion is experimenting with deuterium and helium-3 fuel, which produces less radioactive waste and allows for direct electricity generation. New designs, linear, spherical, and more, are making reactors safer, more stable, and easier to build. The focus is on miniaturization, efficiency, and safety. Key steps toward a world where fusion is everywhere. Each breakthrough brings us closer to a future where fusion reactors are as common as power plants today. The challenge now is engineering, making fusion affordable, reliable, and scalable. We're moving from one-off scientific marvels to blueprints for mass production. The dream: a fusion device that changes the world, not just the lab. The sun in a bottle is getting smaller and closer. Imagine a world powered by compact fusion, cities fueled by clean, safe energy, no greenhouse gases, no blackouts, transportation transformed electric cars, ships, even spacecraft powered by fusion, slashing emissions and opening new frontiers. A small fusion reactor could be the ultimate engine, a portable piece of the sun. The Ark Reactor, wearable power, is still science fiction, but so were smartphones a century ago. Each step, room-sized reactors, then tabletop, then smaller, brings us closer. Fusion's science is real. Its promise is enormous. We're no longer just dreaming about the stars, we're building their power here on Earth. The journey is long, but the path is clear. The question isn't if we'll harness fusion, but when. When that day comes, we'll have brought starlight down to Earth for everyone.